So this will be our lecture for yesterday, Thursday, February 22nd. A couple quick updates. I posted homework 2 yesterday. It's due, I believe, on March 10, so right before the spring break. And I know we discussed the midterm exams, and I sent an email about it, but I was looking at my schedule at work, and I may have to push the midterm till after spring break. Um, but due to some travel. But I'll check on that and get back to you as the month progresses. Um, so today we're going to go over just a couple like examples, and then I'm going to start introducing frequency response using some Bodie-like analysis. Um, so I'm just going to quickly go over the example that we covered in class yesterday. It looked like there were still some questions about it. So I thought that this might be a good avenue to do that. Um, in this example, again, we're looking at just a feedback controller, and we're trying to design a compensator given by this d sub c of s, where the compensator is equal to k times s plus a over s plus b. So there's one pole and one zero, zero at a and a pole at b. Okay, so then using some of the techniques that we learned in class, find these values for the parameters A, B, K of the compensation that will produce the closed loop poles at S star is equal to -1 plus or minus J or I, whatever imaginary variable you want. So we're just going to look at a unitary feedback system, right, where we have an input and we're going to design a controller. We're going to call it d sub c here. And the plant is given by 1 over s plus 2 times s plus 3. So two poles, one at -2 and one at -3. All right. So now as we go through the solution, and again, I did this in class yesterday, but it still seemed there were some questions. So first I'm going to draw the root locus for the system. Okay, so the root locus, if I zoom in here, the root locus is given by so we start at the poles, right? So we have a pole at -2 and a pole at -3, and then the root locus will converge inwards to -2.5 and then expand out from there. And again, I'm going to post let me make a note of that, but I'm going to post a tutorial on how to draw root locuses. I'm not going to require you to do it in class, or in the exam. I'll provide that for you. But it's good to know for problems like this so you can quickly assess whether or not you need to design a controller for your system that's a little more complicated than just a standard proportional controller. So let me make a note of that really fast. And great. Okay, so as you can see from this root locus, we have that there's no proportional controller that'll allow you to design your system such that the closed loop poles will pass through, no, that the poles will pass through the closed loop poles. Okay, again, the closed loop poles are at -1 plus or minus 1 I or J. I think I called it J up here, but I down here, so not consistent, but you get the idea. So we need to do something a little more complicated, right? We need to pick an A and B non-zero potentially, such that we'll curve the root locus somehow into passing through this, right? Great. Okay, so we need to find A and B, which will lead to this root locus passing through the wanted closed loop poles. And we can use the equation that we learned in class, right? This guy right here. So we have the sum of all of the angles of the poles to the desired pole, so that's theta pi, minus theta zi, which is all of the angles of the zeros to the desired pole. And that's going to be equal to 2k plus 1 for some integer k. Okay? Oh, times 180 degrees. Right. So again, we don't have any zeros in the plant of this system. We do have potentially a zero in the controller and an extra pole in the controller. So we get this expression here. So we have theta P1, which corresponds to the first pole, theta P2, which corresponds to the second pole, theta PC, which corresponds to the zero or the pole of the controller, minus theta ZC, which is the zero of the controller, and all that equal to 2k plus 1 times 180 for some k, integer k. Okay, so here I define P1 and P2 as being the angle from the pole at 2 and the pole at -3 respectively. All right, so coming back down here, we'll get that theta P1 will be equal to 45 degrees. Theta P2 will be equal to the inverse tangent or the arctangent of 1 over 2, which is equal to 22.6. Right. And then that'll be equal to, if we plug that back into this equation here, or rather this equation here, and we move over the theta P1 and theta P2 to the right hand side, we'll get that this is equal to 45 degrees minus 26.6 degrees, which is equal to 2k plus 1 minus 71.6. Let me see if I got that number right. Yep, great. So then I just repeated this part up here again. So if we come down from here, if we pick theta c, so we now we have this expression. So now we need to find our theta PC and theta ZC such that we satisfy this for some k. Okay. So if we pick a pole at the origin, let's say, and again, this is because I've been doing this for some time. As you go, you'll get more comfortable with figuring out the best ways to tune your gains or picking your poles and zeros. But I'm going to do something pretty easy for this system. So I'm going to pick a pole at 0. That'll with the desired pole at being at S star. If the desired pole is at S star, let me see if I can write that down somewhere. So if the desired pole is at S star, this will make this theta PC equal to 135 degrees, right? So that's because if I have this system here, I'm going to pick a pole here. My desired pole is up here, right? And so this will be the angle between it. So that's 135 degrees. Again, this is 1i, and this is -1. Great. Okay, so I'm going to set that, and now I just have one more variable to solve for, right? I have this theta sub zc to solve for. Okay, so I plug in 135 here. This gives me 206 on the right hand side. I'm going to pick k equal to -1, which will then lead to this portion of the equation equal to -180 degrees, right? And so then I'll calculate that, and then I'll get a net on the left half side of the system. or the equation, I'll get a negative theta c c is equal to negative 386.6 degrees, right? But if you're for numbers larger than 360 or negative 360, again it wraps around the origin or the reference, um, and that'll give us negative 26.6, okay, which will imply that theta z sub c is equal to, theta z sub c is equal to 26.6, right? Okay, so when this occurs when b is equal to 3. So now we have a 0 at 3. Okay, so now our resulting system here, our resulting controller is given by this. Great. So now to define k, now that we have our system, our controller or compensator identified, which again is equal to k times s plus 3 over s, so one pole at 0 and, one pole at the origin and 1 0 at negative 3, which if you notice that 0 at negative 3, if we go down to our original system here, that effectively cancels out this negative 3, right? So where did it go? Oops. So we scroll back down here. Yeah, so these two will effectively cancel out, right? And then to solve for k, we're going to solve the following equation. We're going to look for the real component of the solution to d at the s that we're interested in over the numerator of our feed-forward system at that point. And remember, our feed-forward system here is going to be d sub c of s times g of s, right? And then this will be equal to some numerator. Oops. Let's go back. Some numerator over a denominator. Great. Okay, so then we just plug in the particular s that we're interested in, and the result is we get 2 for our gain. So then the total controller that we found is given by d sub c of s is equal to 2 times s plus 3 over s. Great. All right, so now the next example is something very similar. We're going to look at, again, a unitary feedback system where we're given the plant, G, and we need to find the controller, D sub C, okay? Where the plant itself is defined by 3 poles and no zeros. So a pole at 0, a pole at negative 3, and a pole at negative 6. And we want to design a lag compensation such that we meet a couple specifications. So we want to make sure that the step response is less than 5 seconds. We want to make sure that the overshoot is less than 17%. And we want to make sure that the steady state error is less than 10% for a step response. All right. So we first note that if we're given the objective to design a lead lag compensation controller, then that has the form same as the form of the previous question, and we need to find A, B, and K such that the dominant poles satisfy the specifications that were defined. Okay. So using the equations that we saw in class, we can find the parameters or the poles that we want to have our closed loop system adhere to, um, using those specifications. So that leads to a damping coefficient equal to 0.5. Okay, and I just plugged that into the equation, that it presented in class, and that equation is negative the natural log of the overshoot, right, over the square root of pi squared plus the natural log squared of, again, that overshoot. Okay, so then that gives us a damping coefficient equal to 0.5. Great. So the next thing that the specifications told us to look for is that we wanted to make sure that the uh, settling time is less than 5 seconds. Okay, so coming back over here, we're going to plug in, if we've given this settling time, T sub S star, and we're going to plug it into the equation. Okay, so T sub S star is equal to 4 over the damping ratio times the natural frequency. Okay, so that'll lead to, at the end of the day, we can trace through this expression here. And at the end of the day, this gives us a natural frequency equal to 1.6. All right, and again, these are just equations that we found in class, and it's just a plug and chug. Okay, so then that at the end will give us our poles that we want to design to, or closed loop poles that we want to design to, equal to 0.8 plus or minus 0.4i. Great. So bring it back in the system. So given that the plant that we're designing to is defined, is given here. So again, that's 1 over s plus times s plus 3 times s plus 6. Okay, and we plug it into that expression that we used in the last example. And so we have theta pi's, we have theta zi's, and on the right-hand half side, we have to find some k to make sure that this is satisfied. Okay, so without introducing the controller, we want to see, without explicitly drawing the root locus, we want to see if we need to actually design a compensator. So if we can just find a k that gives us the values that we need, then we're done. Okay, great. So that means that if what I'm going to do is I'm going to find theta 1, theta p1, theta p2, and theta p3. Okay, which again is just the arctangent of the angle. Well, it's the arctangent of the opposite length minus the adjacent length, right? That'll give us the angle. Okay, so without going through the details of doing that, because I'm going to assume that you know how to. This gives us on the right half side at the end. It gives us 167.32 degrees. Okay, so now if we take the right half side there, which to be equal to just 180, then we get that 180 minus that value 167.32 is a 12.6 deviation. Okay, so that implies that we need to pick our pole and our zero such that there's only a 12.6 deviation between them. Okay, so if we pick our pole at, say, 90 degrees, so directly below the desired pole that we want for our closed loop system, then the zero that we're going to pick is going to be at 77.4. Okay, so, and I show that here. Let's show that explicitly here. So again, if we pick here, if we pick our theta P as 90 degrees, so again, that's directly under the pole, our desired pole on the real axis, then that'll lead to our theta sub ZC equal to 77.4. Okay, so then that implies that our B in our controller is equal to 0.8, and our A here is equal to 1.11. Okay, so then again we have to find our K for our controller. So we're going to plug in the desired pole that we want into the expression. Okay, and then that'll yield 3.57 at the end. Okay, so then at the end of the day, we'll get that our controller is equal to 3.57 times s plus 1.11 over s plus 0.8. All right. Neat. Okay, so I just wanted to run through those examples really fast, spend some time just going through those before moving on to root locus design. But please, if you have any questions, feel free to email me. I didn't go through a bunch of different controller types, although I did provide in the homework where you will look at the different controller types and explain why some controllers will work and some controllers will not for a given system. Um, I for that homework assignment, I just expect 2 or 3 sentences describing why a particular controller type isn't suitable to design the controller or design the system to meet the specifications that were required. So moving on. So now I'm just going to start writing. So now I'm going to look at some frequency response. Okay. So frequency response for a system refers to the case where we're going to consider an input of a frequency and look at the output. Okay. So the frequency, sorry if my handwriting is pretty poor. The frequency response of a system refers to an input. Maybe I'll do this. Yeah. Zoom out a little more. Yeah, that's good. Okay, great. Refers to an input of some amplitude maybe I need to go a little bit bigger. Okay. A and frequency omega, okay, which is amplified or attenuated. Whoa, losing it here. Okay. By some amount and has a positive or negative phase shift. Okay, so what does that mean? So that means that if I'm given it I'm giving the system, so if I have this system here, I'll draw it right here, G of S, right? So this is our plant, like we're used to seeing, okay? And then I'm providing it an input, okay? So now our U of t will be equal to sum A times the sine of omega t, okay? So it's a sinusoidal, again, input. Then as it passes through our plant, we expect that it will be modified in some way, okay? And that modification we're going to say is equal to B times the sine of t. There should be a different omega there. Yeah. Let me make sure that's that. So we expect an omega, I'll put omega prime t plus phi, okay? Where the omega prime is the difference in the potential frequency responses. Potential frequency, theta is the shift of that frequency, and b is the amplitude of that frequency, okay? So if I were to draw this pictorially, let's see, if I remove that, if I were to draw this pictorially, I have, let's say this is my axis here. I'll have my input be something like that. Okay, so this is my input, U of t. And then as it passes through the plant, the output I expect to have potentially some change in amplitude. Okay, so this will be what's called the gain, which is equal to B over A. All right, and then I also expect that, let's see right here. So if I do that again, I also expect that if I give it some input, that there may be some shift in that frequency. Okay, so that shift there is called the phase, which is equal to phi. All right, so now if we come back to just the definition of a transfer function, okay, let me bring back up my notepad there, make that bigger. Okay, so then a transfer function is again defined by the following expression. Okay, we should all be familiar with this, where we have a polynomial on the top defined by a bunch of zeros, and a polynomial on the bottom which defines all the poles. Okay, up until some zm and z sub pn. Okay, again, and if we can write this in a more compact way, equal to k times the product. Okay, so this capital pi is the product sign of s plus zi over the product of s plus pi. Okay, this shouldn't be a surprise to anybody. For I equal 1 to n, and I equal 1 to m. Okay? So if we plug, so therefore, if we plug in a frequency, if we take our pole as to be some s equal to j omega, okay, so omega is a frequency, j is an imaginary number. right? And taking the natural log multiplying it by 20, right? We're all electrical engineers. Here, so that means that it results in the, oops. So this results in decibels, right? In units of decibels. Decibels. I think I butchered that spelling. Okay, but more interestingly, it leads to this. So we get 20 times the log of g omega s. Okay, this will be equal to 20, oops, log k plus 20 times the sum, right? So as you pass, if you pass the product through a natural log function, that results in a sum. Oops. Let's see, natural log of j omega plus zi. Okay, this will be I equal to 1 to m. So these are all a sum of all of the zeros minus a sum from I equal to 1 to n j times of j omega plus pi. Great. Oh, and there's a 20 in front of that and a 20 in front of that. Great. Okay, so this is what's called the gain um, of the system. The phase angle, make that a little bigger there. Okay, so the phase angle turns out to be additive as well. Namely, the phase of our system is equal to the sum of the angles of all the zeros, j omega times all the zeros. So it's from equal to 1 to m minus the sum of the angles j omega plus pi, I equal to 1 to n. Right. Okay. So this is again this is what we call the gain of the system. Oops. The gain of the system. And this is the phase of the system. Okay. So turns out we can compute the phase and the magnitude or gain. Okay, so and what I'm going to do, so we're going to consider an example. Let's do this again. Let's reset that. So in this example, we're going to consider the transfer function, TF, given by just a simple one, right? Just g of s is equal to 1 over s plus, oops, s plus a. All right, so just one pole simple system. Move that up a little bit. Great. All right, so if we want to look at the phase and the gain, or the magnitude of the transfer function, we will need to first plug in. We need to first plug in a j omega. Okay, so first we need to plug in s is equal to j omega. Okay, and again, j omega is just a frequency, right? So this leads to the following. So that leads to g of s, right? Start with what we had. That's equal to g of j omega, which is equal to 1 over j omega plus a. Okay, and that is equal to, if we're going to what we can do is we can multiply and divide by 1, and this will become important in the next step. Okay, and we're going to set 1 is equal to a minus, minus j omega, a over a minus j omega, right? And that'll lead to a minus j omega in the numerator and a squared plus omega squared in the denominator. Great. Scroll up a little bit. Okay, so now using the equations that we had before, we can say that the magnitude or gain of this transfer function is given by the following. So be g of j omega is equal to the square root of the real component squared of g j omega plus the imaginary squared of g j omega, and then this guy I'll extend all the way down. All right, and then that is equal to the square root of a squared plus omega squared over a squared plus omega squared. All right, and the angle of this transfer function is equal to the tangent inverse of the imaginary part over the real part. Oops. Okay, and that'll be equal to tangent inverse of negative omega over a. Great. So we can calculate, so basically we can calculate the transfer function, or not the transfer function, the gain or the magnitude and the phase explicitly. Okay, so this is gain or magnitude. Great. Okay. So now, next we're going to look at what we call a gain and a phase margin. Make sure that the sizing right. Okay, so there we go. So gain and phase margin. So when I say margin, it refers to the amount of gain or phase that can be injected into the system before it becomes unstable. All right, so then some examples of quote unquote gain. So some examples of gain are given by maybe modeling errors, maybe some time varying or stochastic modeling parameters, right? Or also disturbances. Right, so all of these, so now if we look at all of these quote unquote gains, they all have a couple things in common, right? They all pertain more or less to a specific type of robustness. So robustness to, so in other words, we can consider gain margins as a type of robustness to modeling errors if we start with a system, a nonlinear system with parameters that we haven't been able to correctly identify what the parameters are to within a very narrow margin. Then we can design our system and assume that even if our system or subsequent systems, if we're manufacturing them, um, might be manufactured each one might be manufactured differently, so each one has a slightly different model. But we can say that if we have a good gain margin, quote unquote good, right? Gain margin, then we can say that we're robust to modeling errors, or if there's some disturbances like um, wind or noise in communications or noise in our measurements, then a good gain margin will allow our system to be robust to those types of disturbances or those types of parameters. Okay. So next, talk about a little bit about examples of phases or phase margins. Okay, so now things that could affect the phase would lead to a slower or a faster system, right? And also delays, right? So if we have, say, we are getting data at some rate, then our the phase, having a good phase response allows us to say that our system's still stable, even if we don't get those samples at the frequency that we expected it to. Okay, so these are all these examples are called process variations. Okay, so again, if we're making a lot of a specific type of thing, like a widget, then each widget as it's manufactured will be slightly different every time it's produced. Okay, yeah, quality engineering, you look at to make sure that the quality of your product is consistent, but small variations could affect your system. So having good phase or gain margins will allow you to say that if I design my my controller for this product in mind with these parameters, then a slight variations will not affect the performance in a meaningful way. Great. So to define gain margins and phase margins, explicitly, the gain margin is the amount of gain required to shift the crossover frequency, call it omega sub c, to a frequency where the phase is negative 180 degrees. Okay. Next we're going to look at the phase margin. Okay, and that's the amount of phase required at the crossover frequency. So we're going to go at the crossover frequency, omega sub c, to get a phase offset of negative 180 degrees. Okay, so now what does that look like on a Bodie plot? Okay, so let me close that. I think we might have enough room here. Actually, I'm just going to pull it over to the next page. So what I'll do is, here, I'll copy this. All right, copy that there. Okay, so now if I draw my Bodie plot, okay, and we should all remember what Bodie plots are, at least most of us. So again, Bodie plots will have two plots, right? Okay, so then this will be the phase. This will be the magnitude. Okay. So now if I'm just given given the Bodie plots, what's nice about Bodie plots is that you can use them for more or less black boxes. So if you're given this Bodie plot, this is 0 and this is negative 180, right? Then my Bodie plot might look something like this, and my phase response might look something like, make sure that I'm drawing this right. Actually, let me go back. So this one goes down that way, and this one goes just making sure I'm keeping up with where it crosses. Okay. All right, so now we're going to look at where this crossed negative 180, and we're going to draw it up. We're going to look at where this crossed 0, and we're going to draw that down. Okay. And then we have two numbers here, right? So we have that this is up here, we have that this is the gain margin. And we have down here that this is the phase margin. And I think that there's a way to do it quickly in MATLAB. I think it's just Bodie. And that'll pop up with a screen. And we can look at this. We can look at this in class on Tuesday, but it should just pop up with a screen. Where'd it go? Sorry, I'm typing it out to make sure that I'm not lying. Ah, there we go. Yeah, so it'll pop up, so Bodie will pop up with a screen, but the phase and gain margins won't be there yet. So there's another, I'll have to look up the functions for that, but there is a function that will automatically plot the phase margins and gain margins. And then, yeah, so on Tuesday, before going into the rest of this, on Tuesday, we'll look at a little more of Bodie plots and talk about why they're used